Hello, hello, hello. I hope you hear me. I hope this time there's no robotic voice. This time I prepared myself. I hope it's better. I already say hi on the channel and on the chat, so if you will be able to say hi to me as well and confirm that you are hearing me well, I will be grateful. We will start in a moment. We are just right before the second topic in the theme of the AWS Messaging Services. Last time we covered SNS. Today it's time for SQS. So last time we've got push-based services. Today we've got polling services, queues. Hello, Mateusz. Do you hear me well? Okay, so maybe we can start with the reminder what we would like to do over those few meetings that are just in front of us. So last time, as I said, we covered the Amazon SNS. Recording is already available on the channel, so if you are interested to look what we covered there, feel free to join and subscribe. The recording is almost an hour and a half long, and we covered there most of the features available regarding the simple notification service. Today our job is to learn more about simple queue service and learn the most interesting stuff regarding this service and regarding features that you maybe didn't heard about. The same goes with the next meeting, which will be on the next Tuesday, where we will cover Amazon MQ, which is the managed service for Apache ActiveMQ. In 2 weeks from now, we will cover Kinesis data streams, and order of the next meeting is more or less on the slide. We will cover next Event Bridge, managed streaming for Kafka, Pinpoint, IoT Message Broker, and AppSync. Probably there will be one or two additional ones, but we will see how it's going and what are the topics that will be covered, and should we actually continue with this streaming / messaging team, or should we cover and do something different? Hello, Andre. I see people are coming and showing on the chat. Counter is increasing, so I think that we are just ready to start. Once again, a reminder, I'm counting on your active participation, so if you have any questions and suggestions, feel free to do it. Feel free to shout out on the chat in any language you want. I'm recording in English, and if you prefer to ask questions in Polish, feel free to do it. I will translate the question. This live streaming format is all about the conversation, all about the questions. The goal for the whole theme is to going with a deep dive into all those AWS messaging services available. On the previous slide, there was a few of those, and probably some of you know how hard it is to choose the proper one depending on the use case. I would like to highlight what to use in the proper use cases, what are the differences between those services, and I also challenge myself to teach about the less known things regarding those services. So hopefully for each service, even those most popular, my goal is to learn and teach something new that you've probably never heard about. So our today's topic is Amazon SQS, which is a highly scalable, fully managed queuing service. SQS stands for the Simple Queue Service. As I said, is a fully managed service. As name suggests, it's all about managing the queues, but the whole approach is to do it in the most software as a service way as possible. In a basic use case, SQS works as a unidirectional and poll-based service. However, we will talk today about a feature called temporary queues, which allows you for something that may look like a bidirectional communication, and that should be pretty interesting to see. Regarding the features available in the service, we've got two types of queues, and it's already, for those of you who haven't worked with the service in details, it's already confusing, because if we are talking about queues, we should have FIFO, so first in, first out delivery guarantees as a taken for granted when it comes to queuing, right? And here we've got two types of queues, when one has a name standard and one has a name of FIFO. So what's the difference between those two? I will talk about it in details, but there are substantial differences between those two, and it's very important to highlight how they are different. Additionally, in most cases, when you will use this service, you will use them as an internal messaging / queuing rather buses between the components, between the services on AWS. But they can be exposed to the world too. Thanks to the AWS IAM and IAM policies, you can also expose this queue in a fully managed way to your mobile clients, to your applications and other kinds of clients for direct messaging and direct availability. This will help you to build more resilient and less problematic in terms of maintenance, in terms of development services, especially when you are integrating with the client. And funny fact about SQS is that this is the first and very first AWS service that was announced. They did that in November 2004, and that's basically how AWS as a cloud, as a platform started. At this time, it wasn't called AWS, but that was the first service available that started the whole avalanche of other services and created what we are observing and using as AWS. So I split today's meeting in 3 sections. First one is focused on the architecture. Second one is focused on the features, more advanced ones. And third one is about best practices and differences between the SNS and SQS. This part will grow, so you can imagine that if we will be at the end of this kind of theme, we will have a lot of those differences between previous services that we described. I will try to keep this as minimum as possible, and gather this information about proper use cases and guidelines in a different place, probably on my blog. So if you haven't seen it, I would like to recommend it, awsmaniac.com. There you can find the information about future posts and stuff related with this series as well. So in the topic of architecture, we will talk about what SQS really is underneath. I will have a disclaimer later, but SQS is not an open source product, and in many cases we are relying only on the documentation, on the AWS based videos and explanations, blog posts that they are providing, in terms of speculating how it's built internally. But it's not pure speculation and guesses. We can do much more educated guesses. Second topic that I would like to cover is what those 2 different types of queues are, and we will cover that in details. Then we will talk about the taxonomy between the identifiers, payloads, message attributes, and how that transfers to messaging and also pricing. And last but not least, in this section, we'll show a little bit of the use cases that are used by the industry currently. In this section about features, we will talk about reliability and how to handle failures. Outside of that, we will talk about encryption and privacy. We will talk also about two more advanced topics like delay queues, message timers, and temporary queues. And last but not least, we will compare SQS with SNS, and also we will talk about consumption models, because we can consume those queues in two different ways, and also we can use batching. So that will be an interesting comparison between those two mechanisms and how they are transferred to both reliability, availability, and also pricing. So let's get started. As I said, here's the disclaimer. Amazon SQS is not an open source technology, so AWS documents, videos, and blog posts are covering the most technical aspects. However, rest is often a speculation, or rather deduction, much more like an educated guess. Let's talk about architecture. The tagline is already presented, so I don't have anything more to add to that. But outside of having a fully managed queue, we should talk a little bit about how this queue can be available and consumed by the clients. Some of you may be familiar with such protocols like AMQP or MQTT or NMS or JMS. All those protocols are designed for queuing purposes, and they are covered by the Apache ActiveMQ, and on AWS it's available via Amazon MQ. In case of SQS, we have a SQS API that is available via HTTP and HTTPS. So we've got more or less a RESTful API available to access the service and to consume our messages and put those messages to the queue. So if you would like to have an ability to connect the existing systems that leverage the previously mentioned protocols, not HTTP and HTTPS, SQS may not be a best choice for this particular use case. Of course, there are some additional mappings. There's a bridge between JMS interface and for Amazon SQS, and it's very well described in the documentation, but that's not the desired way to how to use the Amazon SQS. Even Amazon itself, AWS itself, provides an information that if you are building something new that will be built for the cloud in the first place, probably Amazon SQS is a good choice. If you have an existing system that have other protocols implemented like AMQP, like NMS, JMS, and so on, probably the better choice will be to use a message broker like Amazon MQ, because you will have less to rewrite and it will be much more beneficial to move those platforms as is to the cloud and then re-architect them when you are there. Outside of the talking about the interfaces and protocols and how to integrate, it's basically a service for decoupling the publishers from the consumers, like in the SNS case. We are removing direct communication line between those two parties and introducing an intermediary. But the main difference between SQS and SNS is that in SNS we have a push-based notification mechanism, which is PubSub. In terms of queues, we rely on polling. So clients are responsible to poll messages from the queues in order to consume them. And internally, SQS has a very interesting, but if you will think about it, it is pretty obvious that it should be designed in this way. But it indeed has very interesting architecture because it's basically a queuing system with a durable and distributed storage. How it looks like. Basically, our queues are distributed on SQS servers and spread around the multiple availability zones, multiple servers spread around multiple availability zones inside a region in AWS. And thanks to that, messages are durable, and thanks to the replication, they are also highly available in terms of, for example, availability zone failure or hardware failure on one or two nodes. When it comes to SLA and durability guarantees, they are pretty high, like for any other AWS managed service. They are basically the same like in Amazon SNS case. So outside of that, that our messages are spread around multiple servers, we don't see that because we connect with our queue via single endpoint. And we will talk about what the endpoint exactly is in a moment. But more or less, we have a single entry point for the queuing system, and the replication and also durability mechanisms are kind of invisible for us. When it comes to the producing and consuming cycle, we can imagine that if the component 1 sends message A to the queue, it will be first replicated to multiple servers across the multiple availability zones. And after that, the message is ready to be consumed by the other parties. So, for example, message A can be consumed by the component 2, which retrieves the message from the queue, and it automatically, when retrieving this message, we automatically start something called the visibility timeout clock. And this visibility timeout clock is pretty important concept that will be present in all later descriptions how SQS works, but more or less it's a reservation mechanism for consuming that particular message. And we can set this visibility timeout clock for a queue as a general attribute of a queue. We can define, for example, that each message should be reserved for 60 seconds, so 40 seconds like in the example you can see on the slide. But we can also reserve those messages when we will receive them from the queue individually. More or less, we are saying that we would like to spend this amount of time on the whole processing cycle. And if we will not acknowledge and delete the message from the queue, feel free to resend this message, reappear this message in the queue for other consumers, because we probably either crashed or this message should be processed faster. On our side, we basically finished in 25 seconds, like in the third scenario, in the third line we can see, and component 2 processes this message and deletes it from the queue during the visibility timeout period. So it ends up in a situation that we basically propagated that change to all the replicated storages, and message is removed from the further processing because component 2 actually handled this properly. As I said, you can imagine an opposite situation when component 2, for example, crashed during the processing, and then the visibility timeout clock hit the 40 seconds, and message reappeared in the queue for other components that will later on consume those messages. So more or less, visibility timeout is, as I said, as a reservation period. Speaking about how we can send those messages and how they will be consumed, we've got two types of queues. One type of queue is standard queue, and according to AWS documentation, this kind of queue has literally unlimited throughput. which means that we can send any amount of messages to that queue, and it should be stored and at least once delivered to the consumers. And here's probably the most surprising part, because it will be at least once delivered, and this kind of queue guarantees a best effort ordering. And best effort ordering means that in most cases we've got FIFO ordering, which is first in, first out, like normal queues that we know from, for example, from the computer science courses. But on some occasions when queue may be overloaded or some servers may be in the maintenance and so on, we may observe a different ordering than FIFO. And that's why it's not guaranteed. And for a very long time, this was not a confusing thing, but basically that was a disadvantage for some use cases regarding SQS. And that's why AWS a few years ago introduced the second type of the queue, which is the true FIFO queue. We have there exactly once processing guarantees and first in, first out delivery, so the real FIFO, but it has a catch. We don't have this marketing world about unlimited throughput. And what does it mean to have a high throughput, you may ask? That's a very good question, because there's a huge difference between unlimited and high throughput. High throughput means that we can have either 3000 API calls with batching, or in other words, 300 API calls per second without batching, if we will ask for just a single message. So basically, it means that it has smaller throughput, but it guarantees exactly once processing and first in, first out delivery thanks to that. And for those of you who worked with distributed systems, you probably feel why it is why the previous type of the queue has the best effort guarantees when it comes to delivery, because it's literally an impossible problem to have a distributed system that will be both available and strongly consistent, because we are entering a cap theorem gray area. But that's not the point of today's video, to delve on the cap theorem. You need to be aware of the fact that those two types of queues are a little bit different, because they are prepared for different use cases. You may ask, why do you need a queue that has best effort ordering? I can give you a great example. So AWS has this very interesting use case. So they created, the company that used Amazon SQS created an app for voting for the like Voice of Poland or superstar TV shows that are available for the audience for voting. And this mobile app has an ability to vote in a very short period of time, that when this particular contestant is on the stage during the TV show. And the standard queue is the best possible use case to present the unlimited throughput when it comes to storing those votes. And that's why they used Amazon SQS. And when it comes to the guarantees, in this particular case, there was no reason to have exactly once delivery and FIFO ordering, because when it comes to votes counting, you don't need to have those guarantees. So those standard queues are very well suited for those kind of use cases when you don't want to and you don't have to rely on exactly once delivery or FIFO ordering all the time, but you have a huge demand when it comes to the spiky throughput, and you would like to flatten out the curve when it comes to those spikes. Because if you will put a queue in the middle of the spiky traffic, you will basically have something that will flatten out those spikes. From the other hand, FIFO queues are also important when it comes to those two guarantees when it comes to processing and delivery, because otherwise you won't be able to achieve this kind of stuff in the other means of work and other services. So the FIFO queues were introduced a little bit later in the process, but still they are delivering one of the most important use cases for SQS. Speaking about architecture and how it's the internal parts designed, each queue, no matter if we are dealing with standard or FIFO, has basically a queue name, which has some limitations when it comes to the constraints when it comes to length and also character base. But more or less, we basically provide this kind of queue name, like in our example, it's my queue. Then we've got two additional elements, which are often mixed, especially if you are dealing with CloudFormation or you are using this in the serverless application model, because there is a queue URL and queue ARN. ARN stands for Amazon Resource Name, and probably if you are aware of and work with AWS Cloud, you know what ARN is. It's basically a unique identifier across the whole AWS account that uniformly identifies this particular resource. And from the other hand, queues can be accessed from the internal or external systems, and that's why they have a queue URL. In this case, you can see that you've got the HTTPS protocol, you've got the domain name, region inside, even the account ID and the queue name. Later on, we will see that this queue URL can also bring some additional information when it comes to the type of the queue and also those virtual queues that we will cover later. But talking about the identifiers, queue can be identified in one of those three ways, where queue URL and ARN are uniformly identifying queues across accounts as well. Additionally, when we push a message to a system, this message receives a system assigned identifier called the message ID. This message ID is also a way to identify this particular message. However, if you will push two exactly the same payloads to the queue, and this queue will be a standard one, this will have a different message IDs. In a moment, you will see that the FIFO queues are actually handling this case in a different way, but in this case, it's basically a additional identifier for the message sent to the queue. Additionally, for each message, we receive something called a receipt handle, and it's not even for message, but for the fact that we are receiving a message. It's like an envelope for this particular receive messages query that we do to the API. And this receipt handle for the message is useful when we need to acknowledge, so delete the message from the queue. Because on this particular layer, we can also handle the conflicts, and we can also see who actually tried to consume the message first, and so on and so on. So once again, this handle is associated with an action of receiving the message, not the message itself. But those identifiers, those attributes are related with both standard and FIFO queues. And FIFO queues have actually some additional identifiers available. First one is message deduplication ID. And this is a token that is used for process of deduplicating the messages that are sent to the queue. And it works like as follows. If a message with the particular message deduplication ID is sent successfully, any messages that are sent with the same message deduplication ID are accepted, but they are delivered once again during the 5-minute deduplication interval. What does it mean for us? Imagine a situation that we have a mobile client that has intermittent connectivity, and it tries to send message to a queue, but it has problems with the connection. So if it sends for this message with the same message deduplication ID a few times, even if the first one will be accepted, we will not see duplicates because it is able to merge those calls with the same message deduplication ID as one and ignore the further ones after the accepted, the first one that was accepted. Bear in mind that the duplication ID mechanism works in this 5-minute deduplication interval, which means that you can observe duplicates if those windows will share the duplication IDs for longer than 5 minutes. If you are using AWS SDKs, that's handled for you and you don't need to worry about. But if you are using some less popular languages SDKs, you need to bear in mind this 5-minute deduplication period. Additionally, you can also add those tokens on your own and try to manage this window and the duplication mechanism on your own with use of that ID. Second identifier that is used by FIFO, it's also pretty important because it guarantees not the first one would guarantee that we won't observe the duplication. This one guarantees the order. So it's basically, the message group ID is basically a tag that specifies that message belongs to a specific group, and messages that belong to the same message groups are always processed one by one in a strict order. And this order is relative to the message group. So it means that if we will see multiple messages in a given message group that are coming one after another, we'll process them inside this particular group. We'll process them in exactly the same order as they arrived. And additionally, Amazon SQS adds something called a sequence number, which is a large non-consecutive number assigned to each message. Andre asks, what is happening to a message if not delivered in the time of 5 minutes? So Andre you are asking about this 5-minute deduplication interval. It depends on the SDK behavior, but I believe a default one works as follows. You retries a couple of times with the same message deduplication ID, and then internally it's returned as an exception, and you need to handle that exception in your logic inside your code and try to either, if you will retry once again, it will be sent with a different message deduplication ID that will have a new 5-minute interval time. So you may end up in a situation that you are retrying over and over again, but with different message deduplication IDs, and finally eventually you will put a message that will have a valid ID. However, if you are seeing intermediate connectivity problems, and in this first message deduplication group, you are seeing that multiple messages actually were sent successfully, but on the client side, you don't see the success, probably you will see duplicates, but across those different message deduplication IDs. So it's up to us how to handle this retry failures on client side. So it's this message deduplication ID, it's for the purpose of the intermittent connectivity problems, not for the handling the fully fledged exactly once processing logic on the queue side. Does it make sense? Okay, so regarding the next elements for the definitions, let's talk about payloads and message attributes. And those payloads are, for those of you who participated in a previous meeting about SNS, you will see a lot of similarities. Payload is basically a message that we are sending from producer to consumer through our queue as an intermediary. Maximum size of a message is 256 kilobytes. It's a hard limit. You cannot go beyond that. You can leverage other stuff like S3 or DynamoDB in order to avoid this hard limit, but it will require to use it in a way that you will store the full payload somewhere else. Additionally, each message is divided into chunks, and those chunks are having 64 kilobytes as a whole, and this is called a request. And one request is the smallest payable element, and you can clearly see that we once again going through the pay-as-you-go pricing model. So as many requests we will see to the queue, that will be directly transferred to our bill. In this case, a full message for 256 kilobytes costs you 4 requests. In US East 1 million of messages for the standard queue costs $0.5, so 40 cents. So 4 requests cost you exactly 1.6 micro dollar, which is pretty low, but if you will have millions of those messages sent to a queue, it will accumulate to a few dollars. Additionally, each message can have attributes, up to 10 attributes per message. This is exactly the same like with the SNS case. However, those message attributes cannot be used to message filtering like in SNS. And that's a bummer. And in order to have a proper message filtering based on the attributes, you need to use SNS. And there's even a pattern when you are actually setting up a topic in front of the message multiple queues, and then you do message filtering based on the message attribute to those particular queues, and you set a row delivery on this topic to not have this nested object SNS wrapped into the SQS and so on and so on. The one catch related with attributes is also the catch related with attributes is that they are adding up to the limit, so you need to be aware of that fact as well. And there is a notion of system attributes introduced as well, but for SQS at the moment we have just one system attribute, AWS trace header, which is leveraged by AWS X-Ray tracing capabilities. So for systems that are using queues, you can also have traces that are spanning multiple services. And even if the message is going through a queue, you won't lose the original trace ID thanks to this message attribute. But other than that, you are not using message attributes on the AWS side. You can leverage them as additional elements. For example, if you are sending from those messages via SNS, that will be a good candidate to to have those message attributes as well available in the SQS. One additional thing related to payload and how this payload is calculated is that SQS counts and computes the MD5 digest of the message and adds this to the message metadata, so to the message attributes as well. And you don't have to be bothered by that, but if you are implementing your own client, or once again you are using SDK in a less popular language, you may face this issue and you will need to know how this MD5 is calculated properly. It's more or less a MD5 of the message attributes and also a payload that is related with the values that we are sending through a message. And last but not least, before we will end up the part 1, use cases. Here you can see NASA, BMW, Capital One, EMS. All those companies are using SQS in various scenarios. So for example, NASA uses Amazon SNS and SQS to decouple various parts of their infrastructure, like decouple incoming jobs from pipeline processing for video and images. EMS uses SQS for IoT device management and communication between IoT-enabled solutions. BMW uses SQS, S3, DynamoDB, RDS, and Beanstalk for managing their informations for the connected car applications that collect sensor data and so on and so on. And Capital One is modernizing their retail message queuing from migrating from the message-oriented middleware to Amazon SQS. So that's the second step that I told you at the beginning. They migrated to a service that is fully managed but still oriented around message brokers and message-oriented middlewares. And nowadays they migrating to fully managed solution that is focusing on Amazon SQS. So in this case, they are leveraging the fully managed and self-managed solution that is scalable and has different pricing models and different availability models. So they are trying to leverage the cloud native solutions. Okay, so we finished the architecture part. Are there any questions so far? If no, we can go further and go with the advanced features. So first things first, let's talk about how to handle failures and how to provide reliability with our queues. So more or less, when it comes to the resilience on the infrastructure level, we are covered, as this is a fully managed service. As I explained at the beginning, you have multiple servers spread around multiple availability zones. On the infrastructure level, we are covered. When it comes to reliability, we need to take care about producers and consumers that are using our queues. So when it comes to the reliability and handling failures, if you would like to reprocess the same message indefinitely, you should avoid setting anything else than a proper visibility timeout. And this will handle a situation when your message should be processed by the broker, by the consumer several times, and finally, eventually, it will be processed properly and deleted from the queue. You need to bear in mind that visibility timeout should reflect the processing time, and it should be prepared not for the average, but for the maximum time that you will observe on the consumer side. That will be a proper way to set up those visibility timeouts. And there is even a guideline how to set up properly visibility timeouts. which is available in one of the videos. I will read out this to you. So basically they are claiming that you should set the 5 times of your give me a sec. Yeah, so for low concurrency, high duration functions, set visibility timeouts to 5 times of your average function duration to avoid sending this to dead letter queue and incrementing receive count retries. And check that visibility timeouts is always greater than the function duration to avoid duplicate invokes. That's especially important when you are working with SQS and AWS Lambda. And even a fraction of errors will induce a back pressure in the situation and interfere with ramping up to a full concurrency with increasing number of pollers for AWS Lambda. So setting up this visibility timeout to a proper value is critical to successful and the least problematic consumption available for your messages. However, if you would like to have the limited amount of retries and reprocessing of the same message, you can leverage 2 mechanisms that combined together will allow to handle this unsuccessful processes. First one is Redrive policy, and second one is dead letter queue. And the dead letter queue again sounds similar to those of you who participated in SNS meeting last week when we talked about an ability to send messages that are not successfully delivered to a subscriber to a particular dead letter queue. And that's basically the same scenario. You can push the message that will be retried and redrive this message to a dead letter queue if the receive count will hit a particular number. And by receive count, I mean how many times consumer try to get this message and process it. So Redrive policy describes you how many times message can be reprocessed, and it is consisting from source queue, received count, that is maximum amount of retries that can be done on the consumer side, and with the DL queue, so another queue that it's set up and that can be a target for those unprocessed messages. And basically they will be held in this DL queue for further analysis or reprocessing. How to move messages out of the dead letter queue then? Well, you can use AWS Lambda consumers and you can avoid writing the consumer logic based on the polling, because AWS Lambda has those pollers available and written for us, and we basically write the message processing code and that's it. Or you can write your own Amazon SQS consumer logic on Amazon Fargate or any other service. And you have much bigger flexibility in reprocessing there. Second topic that I would like to cover here is encryption and privacy. So by default, Amazon SQS has encryption and handled on when it comes to encryption and privacy handled in transit. All communication uses TLS or SSL unless we explicitly omits it, and we can also create queue policies that are enforcing use of HTTPS and disable the HTTP. Additionally, if you are using AWS SDK and the newest versions of the API, you are also safe because they are requiring to use AWS Signature version 4 for authentication and for signing the requests. Additionally, if that's not enough when it comes to sending messages in transit, you can leverage AWS Private Link, which is basically a VPC endpoint that allows you to send messages without sending them via public internet just over, instead you are sending them over a dedicated private link inside AWS infrastructure. And this is basically a recommended way to handle in many cases for many businesses that are that needs to be compliant to a particular standards like HIPAA, GXP, or PCI DSS. Once again, AWS Private Link is the fully managed service, and it's still for huge payloads and huge amount of messages can be cheaper than sending the message via, for example, NAT gateway. In this case, we don't have to be bothered by the NAT gateway, obviously, but in many other solutions and services, private links are a way to go. Speaking about encryption at rest, you are able to use and leverage server-side encryption with AWS KMS, and you are basically passing a customer managed key ARN to a queue attribute. So you can enable this particular queue and encryption on this particular queue. When encryption is enabled, it encrypts the body of a message in Amazon SQS, but it doesn't encrypt queue metadata. So this affects queue name and attributes, the queue attributes. It does not encrypt the message metadata like message IDs, identifiers that we shown, timestamps, and message attributes. So those message attributes that we send, for example, from SNS as well, bear that in mind. And does not encrypt per queue metrics as well. And keep in mind that any message remains encrypted even if the encryption queue is disabled for the queue on the fly. And the same goes with encryption process. So a message is encrypted only if it's sent after the encryption of a queue is enabled. So we do not do a retroactive encryption for the backlogged messages like in the SNS case. So it's very important to remember that that we are basically not retroactively do not encrypt those messages. So the best way and the best practice is to actually enable the encryption at rest at the beginning for your queues if you have such a requirement to be fulfilled. Okay, next feature that is pretty important and allows you for interesting use cases. So there is something called a delay queue, which is basically a queue attribute, the queue attribute that we are assigning to a whole queue that allows us to postpone the delivery of a new message to a queue for a number of seconds. It doesn't mean that it's cached on the client side and it's not stored in a durable way on the SQS side. It's the opposite. When we are sending the message, it's durably stored and written to the disks on multiple machines, but it won't be immediately available to processing by the consumers. So it's a little bit similar to a visibility timeout, but the difference between those two elements is that for the delay queues, a message is hidden when it's firstly added to a queue. So here you've got a timeline that represents how the delay queue is behaving. So when we are sending a message request as a first event on this timeline, we see that message is added to the queue, and then we started the delay seconds timer for the queue. If we will receive a receive message request to this queue during that period, message won't be returned. However, if this period will expire and we receive a receive message request, then we return a message. And when we get a receive message command, we start another timer. This time is related with the visibility timeout, and a consecutive receive messages will not receive this particular message to processing. So the main difference is that the delay seconds affects all messages that are going to a queue, and they will be, thanks to that, message will not be available immediately for the processing by the consumers. But assigning such attribute on a whole queue for all messages may be a little bit constraining. So AWS introduced additional mechanism called message timer, which is a similar mechanism, but it's different in a sense that you can preserve the original queue behavior, but you would like to postpone the message delivery and availability for the consumers for this particular message only. So the main difference between delay queues and message timers is that delay queue is an attribute of a queue, and message timer is assigned to an individual message only. And here you have a much more flexibility, much bigger flexibility when it comes to delivery mechanism. Additional feature that I would like to cover in details is a feature called temporary queue. And this allows us to save development time and deployment costs when to use common messaging patterns such as request response manner. So here's this catch that I mentioned at the beginning, that SQS can be bidirectional. It's not always unidirectional. How does it work? Basically everything happens on the client. So it creates a temporary queues that are virtual. They are managed on the application side, and they are managed on demand for the particular process. Everything maps to a single queue eventually. So you will not see any additional queues that are created on the AWS side, but you will see the request response pattern, and you will have a bidirectional communication line available. So in this way, we can do a fewer API calls and have a higher throughput. And this temporary queue, when the traffic for each temporary queue is low, but still we are sharing a one queue that is having this throughput available, which is pretty interesting if you think about it, how you can handle, for example, those request response patterns, like, for example, subscribing to an email or sending the simulating of the of the user sign up process with the confirmation. Here how it looks like on the example. I know this may be a little bit overwhelming, but let's discuss this in details. So we've got two paths that are related with the order. We've got path that is yellow and path that is purple. Still, we have a single queue named my queue, which is available on the top. I will show you with this pointer that here we've got the host queue, which is available as a single queue in our diagram. And we've got two messages, hello world and WhatsApp, that are sent to a single queue, but they are sent on the client side to a different virtual queue. And this virtual queue is specified by a hash parameter. And if you see a similarity with the URIs and URLs and the hash in the browser, that's a very good analogy to have. So with the send message here, we can say that we would like to use a my queue, and inside my queue we would like to have a virtual queue called my virtual queue A, and we would like to send messages via this virtual queue, and this virtual queue is maintained on the client side only. When it comes to server side in Amazon SQS, all those messages are landing to a single queue, but they are having additional attribute, message attribute that points out a virtual queue name. Then it lands in a virtual queue client on the consumer side. And on the consumer side, we have a dispatch thread that actually fetch those messages. And based on the attribute, message attribute, determines that it needs to maintain virtual queue A and virtual queue B. And we can actually receive the message on the client side from virtual queue A and virtual queue B, which means that we can send message from this place and use channel A to send a message. And you can use a channel B from a client to send a response to the same message via different virtual queue. The benefit of that is that we can create those virtual channels, virtual queues on demand, and they will not affect any, they will just add to a single queue pricing model when it comes to send messages. But if you will send those messages wisely, you will not observe any increased pricing because you will fit in this 64 chunks that are leveraged as a request. Additionally, it enables you a bidirectional communication, so you can simulate request response as well over a single queue thanks to that. Because you can signal a request path over the virtual queue A, and you can use virtual queue B as a signaling for a response path. Very useful thing. However, you need to keep in mind that it may not be available in all SDKs because it's purely maintained on the client side. So it's developed on the, it needs to be developed on the client side. The most resilient and reliable implementation is available in Java. As far as I know, there is one in Python as well, and there's one in JavaScript for sure. So you need to bear in mind that those elements need to be implemented and maintained on the client side. Also, there is a catch related with the reliability. What if our client will crash and we will lose those virtual queues? Again, we need to be prepared on the application level logic to handle such situations as well. Luckily, in most cases, AWS SDK handles that for us, but once again, if you are using a less popular language, you may be forced to re-implement that behavior. Okay, so that will be all regarding the part 2. Let's talk about best practices, and maybe we'll have some questions at the end. Do you have any questions regarding part 2? I don't see any for now. Maybe you are waiting for the end. So let's talk about best practices, and I would like to start with explanation how Amazon SQS differs from Amazon SNS. So the biggest difference is between push-based mechanism and pull-based mechanism. Amazon SNS is a pub/sub mechanism that allows you to send critical message data, time-critical message data to multiple subscribers in a push manner. So it eliminates the need to periodically check for updates. From the other hand, Amazon SQS reliably separates consumers from producers with a durable and highly distributed intermediary, which is a queue, and allows you to exchange messages through a polling model. So consumers have a control over their capabilities, and they are in control when it comes to scaling, and also we can leverage the same separation of concerns as in the pub/sub model. So the biggest difference is between how those messages travel and how those messages are transferred to the multiple parties. SNS is push-based. Amazon SQS is poll-based. Remember that. Another topic that I'd like to cover when it comes to best practices is to use batching. You can reduce costs by manipulating up to 10 messages with a single action, and you can use following actions for that. Receive message, and you can get up to 10 messages with one call. You can send messages in batch, you can delete messages in batch, and you can change message visibility in batch as well. How you can reduce cost in this case? Well, once again, by chunks. If you will think about it, if you will send 10 messages that are fitting in one chunk that is 64K in size, you will pay one request even that you send 10 messages. If you will, from the other hand, send 10 individual requests that are summing up to less than 64K, but you've sent 10 of those, you pay 10 requests. So in many cases, you can actually significantly reduce those costs by leveraging batching. And this affects both receiving part and sending part. The same goes with deletion. You pay for the request to a queue, and if you would like to delete those messages reliably and cost effectively, batching will be a good way to do as well. So bear in mind that it may help you with the price and reducing costs. And last but not least, I would like to talk about the two different polling mechanisms that are available in SQS. First one is called short polling, and it's not a recommended way, because AWS recommends to use long polling, but this one is more for the use cases that are latency sensitive. In short polling, we have very short requests and queries only to a subset of servers, and those subset of servers are done by the random distribution across all those servers that are used for our queues to find messages that are available to include in the response. Amazon SQS set the response right away, and even the query found no messages across those weighted distribution. So it means that we can receive false positives because we may query the wrong subset of servers, not replicated yet, and this message will be available later. But as a result, we can receive the information about the message and message itself much quicker than in the long polling way. So bear in mind that this may be an interesting situation, an interesting technique if you would like to avoid waiting. This looks like follows. So if we would like to fetch the messages in a short polling manner, we basically choose the subset of servers, so the ones with the gradient, so 3 servers out of 7, and when we choose 3 out of 7, we basically fetch those messages that are available in those 3 servers. So you can see that we do not fetch, for example, message E, because it's not available on the subset of the randomized servers that SQS chosen. And maybe in the next short poll, we will be able to receive E, because we will see that we will choose those 3 servers, for example. So that's a drawback of short polling. We receive a much quicker, much shorter, and also much more predictable when it comes to latency answer, but we may receive a false positive. With long polling, we've got much more reliable answer when it comes to the consistency, because we are opening a channel, so a TCP connection that is open and wait for the messages to be pushed down to a client. up to a certain point. So 20 seconds is the max long polling period. And Amazon SQS sends the response after it collects at least one available message and up to a maximum number of messages specified in a request. So we can open our long polling channel for example, wait for 5 messages for 20 seconds. And whatever hits first, it will end up the long polling channel. And we will open another one and once again. Rinse and repeat. But it may send an empty response only if the polling wait time expires. So if for the 20 seconds we will not receive any messages, this polling channel will close, and then we will open another one and once again wait for 20 seconds. It means that we will not receive false positives, but as a result, we need to wait those 20 seconds to receive the messages or receive no messages rather. You may imagine that many people actually employ mixed strategies when they are trying to do short polling and then long polling, but this is basically a very sophisticated request that needs to be supported by an argument in order to provide its benefit when it comes to the complication of the code and complication of the consumption algorithm. So once again, long polling is recommended way to handle messages from the SQS, and short polling is just for the low latency sensitive use cases, and you need to be prepared for false positive in this case. And this is happening because in the short polling, we are selecting only a subset of servers that are used for the replication and distribution of our messages under our endpoint on SQS. And how to enable this short polling? You can do this by per receive message call, because you can set their wait timeout second to 0, and basically that will open a short poll. Or you can set on the queue level that all receive message requests, unless they specify the wait timeout seconds, they will be treated as short polling calls. So you have two ways to actually enforce either short polling on the individual call side or on the queue side as well. And in many cases, you've got those two choices for many settings when it comes to queue attributes, or to the individual call attributes when it comes to consumption, for example, or sending a message. Okay, so do you have any questions? Please let me know. I hope that you have learned something today that is interesting and something new. I hope that especially the part with temporary queues can be surprising, because in many cases we learn that SQS is unidirectional, and here we can simulate request response pattern with the virtual queues. I think that the pretty interesting part is also related with the delay queues, and short polling is not always the recommended and the well-known option as well. Okay, I see that Andrew said that there are no questions, so I think we can end in this way. That's everything what I prepared today. If you would like to have more questions later on, you will remind something, feel free to reach me out on LinkedIn or on the Slack channel for światchmury.pl, and see you soon next week on the Amazon MQ meeting, when we will discuss the other message broker available on the AWS that serves the purpose of the hybrid cloud infrastructure connectivity, and it's also recommended as an intermediate step between leveraging the SQS in the cloud native applications. But when you are migrating from the on-premise environments and you have already a message broker there, it's good to actually implement Amazon MQ in the first place. So thanks a lot for today's meeting, and see you soon next week. Cheers.